Hi, and welcome to this session on part 3 of the Learning from Disasters, with a little bit of focus on FMEA and HAZOPs. So without further ado, we'll get going. So similar to the aims I had earlier in parts 1 and 2, just a little bit more focus this time on the FMEA and HAZOPs, but continuing also with some of the theories, particular the links between maintenance and reliability, because it's a major part of what we're looking for in risk management, should we say. So very briefly going through, if you think about maintenance, how it's developed over the years, you can see there in the timeline how the focus in the third generation tends to look at, rather than waiting for something to break, is actually getting ahead of yourself and plan preventative maintenance issues that are put in place to try and avoid, should we say, but also with this aspect of reliability and perhaps, should we say, life cycle of different products and pieces of equipment and so on. So you can get more out of it over the longer period of time. So there's changes that have taken place, and there's been different views that have had to develop over a period of time as well in that interpretation. But nevertheless, some new ideas came out, like condition monitoring and planned preventative maintenance. But within that, you've also got some theories around the people involved in doing maintenance, and the multi-skilling aspect, to make sure that all areas that perhaps could go wrong are thought about. So definitely the studies around HAZOP, failure mode effect analysis, and also fault tree analysis have been used for many years in high-risk environments, particularly at the design stage, but also, rather than just focus on reliability, looking at maintainability of the equipment as well. Where is it? How is it accessed? What resources do we need? What kind of environmental factors could perhaps increase corrosion or other areas around that can then elevate the need for maintenance more often? And I guess if you link it to things like lifting operation, lift equipment regulations, you could perhaps see how legislation has been brought about in a variety of different areas, like pressure vessels and their regulations, lifting operations under LOLA, and so on. So to be able to say, tighten up the standard, make it better to prevent disasters, excuse me. So challenges around maintenance have been there for a long time, and it does come down to the evolution, should we say, of management attitudes towards the need for improving maintenance in order to improve reliability. So that's the kind of idea behind that. In terms of what we look at, we perhaps have redefined what maintenance was, and as a result of that, putting more emphasis on the planning behind that, rather than just focusing on correction and sorting things out after the event. With the amount of incidents that take place, there's also the aspect of what happens if. So the emergency maintenance is also important, because people have had a lot of accidents whilst undertaking maintenance related activities. And there we have it, that's how it relates to reliability. So various forms of maintenance have come about, and there are different types, but nevertheless, they all are trying to work towards a better way of doing maintenance. Some companies, particularly high risk areas, will have all of these types of maintenance. Others will just have the planned preventative maintenance, where it's reliability is not a major concern. But I guess the higher the level on safety criticality, the more reliability centered maintenance is necessary to make sure that things don't go wrong and leave you in a disastrous situation. Maintainability is a new word that came in the 1950s, but it's been developed and evolved as well. So it relates to inherent attributes of the design and how to isolate the energy sources, others surrounding items and the environment in which they are situated. So again, the links to perhaps corrosion on some materials, influenced by the provision of the appropriate staff and facilities necessary for controlling and carrying out the work. So again, you look at some of the disasters and the learnings from that, you can see how inadequate the management's attitude towards having the systems in place, safe systems of work or standard operating procedures, but also making sure that they were effective. And then in making sure they were effective, the reliance on people and knowing that they were capable of acting in the manner expected in the crisis situation. The factors affecting maintainability are quite wide. Inaccessibility as well as accessibility, how modular it is, different parts that can bring up the overall finished product. State indications, you know, where are we at? What does it tell us? What alarm systems? What are signals are there that says it's isolated, the power is on, the power is off? If in one of the states, what can happen? Could it result in a safe position or failure to safety, or could it leave it in an energized, unsafe situation? So indication is important to be able to identify what to do in various parts of the maintainability aspect. Test and diagnosis facilities are important because we can give accreditation over the years and years and historical information around different equipment, switches, materials, in a variety of different circumstances. We then realize how reliable or unreliable they are, and we can use that information to then set and plan the need for replacement, spares, and extra resources and tooling in some cases to make sure that you're quick and efficient in the manner of maintenance as well. It's been a big part of legislation for quite some time now, but just to go back, under section 22D of the Health and Safety at Work Act, if you're going to provide anything, safe plant, safe equipment, safe systems of work, safe people, etc., it needs to be maintained to remain safe. And that general duty means that anything you provide in the interest of safety must remain safe. More specific requirements in the management regulations about the interpretation of what maintenance could lead to accidents and the significant risks associated with that. But there are other requirements, the workplace regs. If you're going to have an absolute duty on floor surfaces, therefore there's a need to maintain, and it says it in the workplace regs, maintain to a fit for purpose standard with your floors, your gates, your environment as well, the workplace. Personal protective equipment, even so now with the revised version of the PPE regs, with more emphasis on credibility and reliability of personal protective equipment and respiratory protective equipment. So the employer now has to show and justify that the equipment that they're used for the personal protection does the job. It's got to remain fit for purpose. So once you provide it, there's more emphasis on the need to clean, the need to store and maintain, followed with, if anything is unrepairable, it must be replaced. Work equipment, well, it's big in work equipment regulations, so I'll talk a little bit more on that. So regulation 5, efficient state, efficient working order, and in good repair. It really is as simple as that. When it's explicitly written in the legislation that we have a duty to provide something that is fit for purpose, then these 3 statements are now saying remains fit for purpose, efficient state, efficient working order, and in good repair. So it all links to maintenance. And therefore those 3 items, employers have to justify their decisions around that, and also they have to have records that show that they were doing what they said they're going to do, and that can be planned preventative maintenance that will show a schedule, and also a record saying that we've done these on a regular basis. And in COMA sites, it's an expectation. If you want your license to operate, then you have to show these records in order to be audited independently. So we consider a variety of different types of work equipment and the various states and situations they may be used. So checks are carried out before use, during use, and after use. And do they remain safe throughout? Have we considered the efficiency and performance of those pieces of equipment? and generally are they in good condition. Further, it states that we have to keep a record of the work that's being done to show that maintenance is taking place on a regular basis. It then goes on even further in Regulation 22, explaining what must be done to do the maintenance work in a very safe manner. Again, because there's been so many incidents whereby people have had accidents, bad accidents as a result of not following procedures or not isolating or not having tag out procedures and so on. It focuses on minimizing risk to themselves, the maintenance engineers, the employees, more so than others. There are three parts to Regulation 22, sorry. The operations will, while the equipment is shut down. So can you do it whilst it's isolated and remains in a safe state? So valves are closed and locked off, electrical energy is turned off, switched off and locked off and so on. Measures to ensure safe maintenance while equipment is capable of moving. So let's say a press, for example, and the press is an impact press, so it can come down. If you lose energy, you would need perhaps a physical restraint, a chock, so that a block of wood perhaps or something else would stop it from coming down and therefore remains in a safe state. If you think of it differently, if you have something like a switch that when you lose power, it has a mechanical link and it brings something in, so at the top of the press it stops, or you have another mechanical switch further down or another one further down, but no matter where it is, the press stays at that position in a safe state until energy comes back in, the switch goes down, and so does the press in a controlled manner. So looking at it in terms of variations on what could go wrong. And that's where failure mode defect analysis comes in and fault tree analysis, because you can identify these things at the safe stage, should we say, at design, the early life cycle of that maintenance activity to make sure it's capable of remaining safe. And then also protecting all employees who carry out the maintenance. So the classic example would be, rather than just issuing personal protective equipment for maintenance engineers, if they're doing electrical work, it may be you need a rubber mat so they've got extra insulation. It may be insulated tools so that the electric shock can't actually get to the hands, should we say, and so on. So thinking about the process to make sure that people who are doing the work can do it in a safe way without exposure to unnecessarily to the hazards. According to the situation, employees need to comply with at least one. Yeah, so it's written in the regulation in the ACOP also as an interpretation. So if you want to, or where you can, cover all three, but if you can't cover all three, a minimum of one must be covered. Measures to ensure safe maintenance while equipment is capable of moving could include guards and barriers, controls that limit or slow down the movement. Now, a lot of machinery has inching, that you can press the inching button. So let's say you've got a cylinder that's rotating round and you've got another cylinder underneath. If the hand came in, it will be a nip or a pinch hazard. So if the guard stopping the two rollers coming together and causing that inward nip and then fracture and amputation in some cases, if you have to remove the nip guard and you've got the roller going around there and a roller underneath doing the drawing, you would have what we call an inch. So you put it into its inch state, you press a special button, turn it, the switch, and when you press the button, it only allows it to increment a small amount, so that it's unlikely then you can draw in, because as it draws in perhaps the fingers to the edge to get caught, you can then drag back and then say, oh, and again, you think your other finger is on the control switch whilst you're inching around. So it acts as a distancing mechanism to stop you from becoming exposed to the hazard or the danger zone. Remote measurement or alignment instruments that can mean that you can get sensors built into it, or you can measure from a distance rather than being in the danger zone yourselves. When we look at protecting employees carrying out the maintenance, it can be achieved by, again, barriers. So only the right people, the authorized people doing the work. Safe controls in terms of getting in and getting out. That always reminds me of the bad incident where people in a bakery died. 2 maintenance engineers were burnt to death because they didn't allow a good 24 hours for the oven to cool down. And for some reason, there was a one-way system. So you could go in, but you couldn't go out the same way. You had to walk through the center of the oven in order to get out the other side. I don't know what was going on there, but it meant that they walked to their death because it was too hot. By the time they got to the center of the oven, they were overcome and heat exhausted, and then they cooked, basically. So again, think about getting in and getting out of as such. And then, as you see, as is most cases, PPE and other equipment that protects the individuals as well. And then with maintenance operations while equipment is shut down, sometimes you can do that and you can de-energize it and it'll still be in a fail to safe mode, but it's not always the case. So the best solution if equipment can be shut down is to shut it down or make it inactive before the work is done. And in the back of my head, I always think of the time when there was a jam inside. It's like a giant shredding machine, for want of a better word, but we had lots of scrap paper going through and there was a jam. So in order to get the shredder to cut the paper, the big bolts of paper to continue, this guy heard the noise and I heard it as well. So I was slowly sauntering along to investigate. And at the time, the engineer had already climbed inside it and was kicking the big bundle of paper that was causing the trap. As a result of that, if he'd have released it, he thought, well, if I just get in there and release it and get it over with, they can then carry on because then I could jump to one side and I'll be okay. But if he hadn't released it, his leg would have been caught and it could have drawn him in and he could have had, his whole body could have been trapped in the system as well. So it does worry me in terms of people reaction, should we say, the human factor, thinking that if I intervene now, I can save myself a lot of time. So it's always better if you can shut it down so that it remains in a safe state. And whilst it is shut down, perhaps you can cut away and get rid of the jam. But that comes down to efficiency and reliability as well. Regulation 19 of PURE covers safe isolation of sources of energy. And, think of it pneumatically, as such, oil under pressure, as gases under pressure, as well as electrical energy. When it is isolated, it needs some kind of lock-off procedure so that people don't interact with it and bypass it or put something into there that makes the situation worse. So in Regulation 19, it focuses on suitable means of isolation. So the higher the level of risk, the more guarding principles need to be in place there to stop people overriding it. Their identification and accessibility. On a small machine, I had a guy who broke his arm once because he bypassed the interlock. And by bypassing the interlock, it meant that this table that goes from the ground position to the upright position, it was in the upright state and he bypassed it whilst it was in the upright state. When he opened the guard up, it stayed there for a while, and then when he was doing fault diagnosis, it dropped down. And it dropped down on his arm and broke it. It could have been worse because if there was a shear edge or a sharp edge, it could have been amputation. So there's this aspect of what you do and what you don't do inside the danger zone, and therefore people need to know this and needs to be identified as well. There's also the issue of overriding and bypassing safety switches, interlocks, and the situation that could lead as a result. If he'd have isolated the whole machine and de-energized it, then that plate couldn't have moved down. It would have stayed in a safe state. Reconnection. So towards the end of the work, you're doing some preparatory work, and sometimes by that reconnection, it can partially energize or put some pneumatics in place that put pressure against a valve. It could be a variety of things. It could be electrical work, and while you've reconnected the electrical work, you've now created the full loop. on the circuit, and therefore it's energized. So again, when we have reconnection, it's important that we think about what can happen, what could go wrong. And again, failure mode effect analysis is very useful in these areas to identify that. Other aspects of regs, so inspection, so checking to make sure it remains in the state expected. Specific risks to people that may introduce new risks, and maintenance is listed in there. Information instruction, so that people do it in a competent manner and follow the rules, as is training. Lighting, so that if you're going inside a machine or a confined space that's not getting natural light there, then perhaps you need artificial light so they can see what they're doing and can do so in a safe manner. So that's the aspect of the regulations. When we now look at other aspects of maintenance, quite often you get written schedules, so it indicates how often you're going to do the type of planned preventative maintenance. It also includes the procedures and how you're going to be doing it, so they can be evaluated. It stipulates how often, who does it, and the hazards. So this is very much a risk management approach, and it's part of planned preventative maintenance nowadays. It also gets people thinking about the component parts and also the monitoring. Again, going back to aspects of reliability linked to maintenance. The high critical piece of equipment need to remain reliable, and therefore, if they're not, more maintenance is required, more inspection is required. So look at those and identify where the life cycle could impact on this. They need to be high performers, need to have a long replacement delivery time. If they do have a long replacement delivery time, then you need spares so that you can immediately replace rather than put others at risk, or taking shortcuts, or putting something else in place that's perhaps inadequate. Again, the higher the level of risk, the more you have to rely on these things, because it's just not worth taking the risk. Components are indicated by experience to have a lower life than the rest of the machine. So again, thinking like lifting operations, lifting equipment regulations, really, the weakest link takes priority. So even if you have a 5-ton overhead crane and you have the hoist attached to it that can take 1 ton, it may well be that you have component parts like a shackle that can only take 1/4 of a ton. Whatever it is, the smallest lifting capability becomes king, and that becomes your safe working load. So again, it's looking at using that kind of technique to build that in with the experience, so you can identify, well, if we're relying on something and we have to replace it, how long will it last and what could go wrong? Then think about the machine. What are the consequences of such a failure? If so, more reliability is expected. Dangerous materials could be released, and the machine is used for transporting personnel. So again, if you're moving personnel, there's higher risk and therefore higher standards expected. So RCM looks at it from, again, reliability is built into the title. So it says, let's maintain that reliability. That's what it's all about. Keep it operating to its highest standard. And there's 7 basic questions: functions, associated performance standards. Fail, how can it fail? What causes it to fail? When it does fail, what occurs? And what do we do about it? And what does each failure matter? How bad is it? Can we live with it, or do we need to take extra precaution? What can we do to prevent the failure? And then what should be done if a suitable preventative task cannot be found? Now this, and the reason, one of the main reasons I put this in, is to link it to failure mode effects analysis, because this is very, very similar to what that tries to do. It's identifying where it can go wrong, the consequences of it, and the link to reliability. So in higher risk environments, it's expected. It's used a lot to improve performance, more cost effective, speculating to accumulate. Some would argue that that's not the case, because you end up with a lot of components that are in the stores waiting to be used for longer periods of time. But there is the issue of expensive items being stored. Comprehensive maintenance database So it shows you each little part and how much of those you'll need in your backup. Greater motivation of individuals, better teamwork as well. So all of that are the benefits of it, condition monitoring. The idea is to look at what it is at the moment, how good is it, how safe is it, how economic is it, and how can we prevent or improve that by maintenance. So typically you can use a variety of methods, but thermal cameras are great for the top one there. So if you use a thermal camera now, you can see when a part is overheating. So that's good. Also, there's the smell, using your various senses. If you think about machinery in particular, they have a certain noise. And when it's running well, you know what that noise is. When it's not running well, you can do a comparative, and therefore it helps you to identify malfunctions. Feel, hot to touch, cold to touch, vibration parts. They're also useful in terms of saying perhaps the damper's not secured as much as it should be, getting more vibration, more resonance. So there's linked to noise as well. And then your general sense combined to assess the machine performance. So that requires quite a skill and experience involved there. And one thing I do mention to people is, as let's say you get to the end of somebody's retiring and you've relied on that person for a long, long time, if you haven't had a good handover with say a replacement person, you can lose those skills, but you can also lose that experience. And that experience has with it the use of those senses to be able to predict things more quickly. A key part about monitoring as well is to have instrumentation that gives you the information you need. And this is big in high-risk environments. So it can tell you from the display unit, should we say, when things are or are not the way they should be. You know, think about rails, for example, and the links to signals. You know, if the signal says safe to go, if the signal says slow down, or if the signal says stop, then that instruction is seen in a variety of different stages as the train is driving along the track, and therefore action can be taken appropriately. That's the idea. You know, same thing can be done on any control pressure, control panel in a high-risk environment. It is going to persuade by using the senses to be able to allow the operatives and the maintenance engineers to identify whether the machine is working safely, and it's giving you information that you can respond to. So instrumentation plays a big part on that. And from that, what they can do is use the information to then say, as a smaller version of an FMEA in some respects, is to plan the senses as such. When I hear this, when I see this, when I feel this, it will tell me something about that machine. So if you do a log diagram of that, you can see how the methods of monitoring of machines and components can be used. The information can tell you something. And quite often now, the handheld instruments that engineers carry around with them as the information that they need to be able to diagnose. And this is exactly the same. All they've done here is put it into a chart, whereas if you did a typical detection system of faults, you'd put in the information in your handheld unit and it will come up with, have you checked this? Have you identified this? Does the light show green or red or yellow? You know, what is the state of the information? And you go through a series of diagnoses and you end up identifying what's wrong or typically wrong in that detection. So condition monitoring is an important part of analysing equipment to then give the appropriate maintenance. The next one is checklist reviews. And I guess the downside to checklists are you focus just on what's on the checklist. For some, if you're using contractors that are coming in as specialists to look at maintaining a piece of kit, then quite often you can get them, how should we say, managing the situation with over information. You know, what bullshit baffles, that kind of approach. So, you know, the cowboy would say, oh, there's this wrong. And if they get an answer back from that, they'll say, well, there's this wrong as well. They'll constantly add to the list of issues. So bear that in mind in terms of the competent person doing checks and what's actually needed on the checklist, because if you only view what's on the checklist, you're only getting part of the overall picture. Longevity might be that you've not looked at one part for 3, 4, or 5 years, and that could be safety critical. So it looks at the program and formalizes it. It looks at the maintenance department and what they do and what they don't do in the plant operations, and what's needed from a reactive and how you can be more proactive. Are maintenance personnel available when they're required for a variety of operations? Certainly from my experience, I've found that the maintenance team have been on all shifts regardless, and you always had perhaps a pressure specialist, a fitter, electrician, and maybe one other, dependent on what the areas of specialism were, to make sure that if anything cropped up that was problematic on that shift, there was a team available to be able to respond. Interestingly though, as we go down the route as they did in the 1980s, was multi-skilling. And some would argue that an electrician who was multi-skilled, trained to become a fitter and everything else, was probably okay, but sometimes the other way around didn't work. A fitter trying to be an electrician perhaps didn't have that capability. A long-standing issue and argument, should we say, in a variety of maintenance teams. But again, be aware that capabilities and competence is an important part. So how do your companies check competence, particularly when it's safety critical at high risk environments, and recognizing people's limitations, and again making sure there's sufficient resources and people to be able to respond to any incident. Is it usually operating in its optimum position and optimum design range? So what we're saying is, think of a speeding car really. If you're going at 56 miles per hour, that's the ideal. But how often do we get the opportunity to drive at 56 miles per hour? And therefore the range might be from 0 to, I don't know, a high performance car, let's say 120, that's your range. But in reality, the majority would be a lot less than that. So 70 miles per hour is perhaps the limit at the upper end, and at the lower end, it's 0. So when you're going outside of the parameters, how does that affect the reliability of that engine, of that machine, of the equipment? And can it increase risks, particularly around reliability? Some would argue that quite often you need to get on the motorway and blow out your engine at 80, 85 miles per hour just so it gets running as it should be. Do you do that in the workplace though, with equipment whereby you know that if you put it on full pelt, that's going to help the bearings get lubricated and warm up? Maybe so, but it could also take it towards its limits. Similarly, if you look at lift and operation lift equipment regulations and the need for thorough examination on lifting equipment, let's say a forklift truck as an example, if you push it to its limits, which we're asking the examiner to do, they take in a load, let's say it's capable of lifting 2 tons, they would work out the safety factor and say, well, I need to push it to 2.5 tons. So they'll bring 2.5 tons of weight with them so they can do a thorough examination. And they'll do non-destructive testing techniques as well. But nevertheless, it's pushing the parameters to see whether there's anything's going to buckle under those strains, knowing that it shouldn't, in normal operating capacity, it shouldn't come to those extremes. Questions asked: has it degraded the equipment? Has extra forces been applied during operation? And how does this affect the design parameters as well? Ultimately, does it remain safe after that? And who determines the repair or replacement of equipment? Key thing there, if you look at the incident in Cumbria, where they had Legionella, that director of facilities, she decided to change how she was using her budget. So let's say there was £50,000 a year put aside for Legionella checks on the air conditioning units in that shopping area. She decided to take that away and use that 50,000 somewhere else. As a result of that, it wasn't getting the checks it needed. And also when the bacteria, Legionella, built up, it built up to a severe level, and therefore 80 people were affected by it. You know, so the key thing, I guess, is who determines how the budget is used, as well as how often the repair takes place and how often replacements come in. Because when you look at critical aspects of safety, you increase your reliability checks rather than the other way around. And if you decide to decrease, well, you only have to read some of the disasters. And this has been a key factor in some of those disasters. And then finally, looking at what's out there on the market and the technology that's available. There might be better ways of doing things. There might be micro gauges. There might be other ways of doing it more efficiently and perhaps with knowledge. So keeping abreast of things, upgrading equipment is important so that it becomes more reliable. And then from a management perspective, how is that all used? And how is it recorded? And then from that, how does it define what we do? And that's the approach, should we say, on maintenance checklists. It determines that preventative maintenance program. And then people, the people bit, the culture of the organization, the capabilities of the people doing the maintenance work, the limitations, as they age, you've got experience going in greatly in one direction. On the other side, you've got an aging workforce that perhaps capabilities should not put them under as much pressure. So there's all those aspects that need to be considered as well. Now, in terms of what maintenance is, it takes account of all of these tasks, and therefore we've got to think of those tasks in terms of what if. You know, am I doing bits and pieces? Am I doing standard stuff? Is it simple work, or is it quite complex? Is it testing? Is it pushing me to the limit? So ultimately, it's going to bring something back to a good operational state, and in some cases better, because you've maybe replaced bits with better technology or better materials than previously were in place, and therefore the longevity of that piece of equipment is improved. So no matter what the task is, it has to be thought about from the potential of something going wrong in terms of safety. Conditioning is one of the activities associated with maintenance. Now, the HSE have done a few studies on high-risk environments. One of them I've just pulled out. The report's been around for about 15 years now, but just shows how things can go wrong in the field of maintenance. And as a result of that, they did a lot of research in the area. So typically, people are hurt by those reasons whilst doing maintenance, and you can see the statistics on the left-hand side. So the release of pressure, dropping things, coming into contact or being hit by, release of chemicals. So you can see it's all tick, tick, tick. Yeah, I can see that happening in a chemical industry as such. They looked at the times involved in it. Quite often, it was during the maintenance work rather than the preparatory work or the bit at the end. But nevertheless, the consequential aspects of having done the maintenance, there were still accidents in those areas as well. It led to thought processes around how we can prevent, and as a result of that, it looked at formalising safe systems and putting permits to work in place. And those permits to work had a major impact on the industry, but it did slow things down a lot, and some people were reluctant to use permits to work. However, from a safety perspective, it meant that equipment was isolated properly, it was purged if it needed to be, the handover of the competent person, so the responsible person can hand it over to a competent person, a maintenance engineer, a contractor, and they become then personally responsible. And then when they hand it back, they ask back, the responsible person says, what safety protocols have you followed to bring it back to a safe state, and so on. So it really did formalize an organized way of doing safe systems. It thought also about protective equipment and its limitations. And quite often, in a high-risk environment, chemical industry, they identified that personal protective equipment wasn't being used as often as it should be. In some cases, it was inadequate, so it wouldn't protect them from the hazards exposed. Take respiratory protective equipment as an example. Some people were using filter masks in an area where gases were present that would mean your oxygen depletion was there. So they should have had breathing apparatus in place instead. So a lot of thought was gone into that in terms of the efficiency and effectiveness of protective equipment. And then also thinking about the results associated with incidents from defective equipment. Quite often, as we've seen from disasters, it was poor design and construction, poor installation, and also poor maintenance. So therefore, more emphasis and more time was expected to be on those three categories to prevent disasters. Learn from disasters. Yeah. In terms of machinery, inadequate guarding or lack of. In terms of the place of work, think about the access and egress, the working platform and the variations on that. Housekeeping was constantly an issue with maintenance in terms of people falling over things that they'd, let's say they'd take the guard off, put it on the floor, and then they're falling over it. If they're on a platform, they'd fall from height and so on. And then they need to look at the people side of it, information, structure, training, supervision, so you can make sure you get the right behaviors in place. So people were incompetent and they didn't have the right training, and then the supervisors were incompetent because they didn't know what to look for. So if you put all that together, excuse me, it says that the chemical industry had big problems because high risk environment like this is, there was a culture of not focusing on what was needed and not taking safety as seriously as need be. There's also this latent decision-making process that created increased risk. What's going on there? So if you have a system in place, you should be able to then say, when something goes wrong, what do we do? And do we take out of commission certain parts? If we do take it out of commission, how does it impact on the hazard? If it impacts significantly, what's their backup plan? And therefore a safe system needs to be in place for that. Also, when we're doing testing, when we do the testing to make sure we're running it back in or bringing it back to its original standard, things can go wrong then. So do we have to make sure everybody's moved away from the area so they're not put at risk? The reductions in and the strains on maintenance resources. So as years go by, they realise that it's a large cost to keep maintaining these to a high level, and therefore they've reduced the budget, they take shortcuts, they change the personnel involved, and that adds to the level of risk. Changes in the way they were doing things, ill-considered changes in the preventative maintenance schedules, and demands put upon production to get it back as quickly as possible because finance dictated that that had to take place. So this attitude of commercial interest being the top priority. So I wanted to start off by showing that, to say reliability and maintenance influence some of the activities in risk management. I hope I've managed to show that before I now go on to HAZOPs and FMEAs. So I found a really good article that was done by someone from TNT. So I thought, why not use that, because it's a good document. It gives us a great understanding, shall we say, of what hazard and operability studies are and what they do and how they're used. So it enables teams, and I guess the design team is a key element. You can see where it fits in the life cycle of a piece of equipment and also a process, but it should be from the beginning. when we're building these multi pressurized systems and high risk environments, if we get it right from design, then it should reduce risk thereon. However, you've got to keep that concept going throughout that life expectancy, all the way through to demolishing it and, you know, decommissioning it, because there might still be hazards inside the equipment itself when going through decommission. So the process enables the design teams and others, so it's at the start of the phase, but it's also further on, to predict where failures in the systems might occur, and then proactively take action to mitigate them, so it doesn't become a disaster. That's the key thing. It allows you to manage the risk appropriately, and it's usually done from a project management perspective. So the start of the project through to the end. Yeah, and now those are the variations that we're looking for. So this particular study, or one method, should we say, it's been around for quite some time. It was developed from over 50 years ago, and eventually you've got a variety of standards that are out there. So if we look at the IEC 61882 standard for chemical, engineering, petroleum industries and process, and it then sets the standard, as is the idea, so that people can follow this in terms of how it works. So 61882, it shows the technique of a defined system, the objective of identifying the risks associated with operation and the maintenance of the system. So again, bringing us back to maintenance. The hazards or other risk sources involved can include both those essentially relevant only to the immediate area of the system and those with a much wider sphere of influence, for example, environmental hazards. And then also potential operability problems. Yeah, so now we've gone beyond just design stage. We're saying once we're in the thick of it, we're using it on a regular basis, what could go wrong? And if it's bad, then we need to put our backups in place to say what if and how can we deal with this, emergency response and so on. So it usually involves a team of people, and it's done at the design stage or as early as possible in any project to think about what needs to be brought about in terms of additional costs and resources so that you can control and mitigate. It's when considering any major modification to assess the safety of the proposed changes and any effect on existing plants. So again, as much as you've done something at the design stage, you may be redesigning it or you may be changing the way you're doing things. And as a result of those proposed changes, what impact does it have on the existing plant? So it's that opportunity then to say, it's not just for designers, it's further into it. Because as what I've said before, you learn things from the latest version technology that's out there or changing the way of doing things, better ways of doing it. If you're going to put that into the plant, then you need to use a HAZOP. It can cover the whole site, it can cover parts of the site, cover specifics, but nevertheless, it's a great system to use. And it's easy to follow. You know, you've got those 6 or 7 stages, should we say, that help you to have a methodical, logical approach to it. So concept all the way through to operational phase. At each phase, the outputs and the requirements identified from the previous phase are verified and validated. Yeah, so they keep this what if approach to it to say, and then go back. Well, if as a result of that change, if we implement that, how then does it impact on HAZOP stage 2, where we hadn't thought about it until we got to HAZOP stage 3. So go back and make some influence and changes there. So those are the typical stages. You need a good team. They need to know about how to use nodes, should we say, similar to fault tree analysis, and then how it fits into the line diagrams to then be able to develop it further to look at the concept, but always focusing on what happens if. So at each node, the key parameters are investigated for the deviations from the design intent. Yeah. So it should be reliable, it should do the job, but what if? Yeah. So what can cause it? Give an example here. a strainer blocks, and due to its impurities, you know, the water might have been going through, and it's not had a filter in it, it blocks in tank T. That might cause an effect on the flow. Yeah, so you've got a strainer that's not doing its job as a filter. You've got the tank that's now potentially blocked. If that blockage now causes a buildup of pressure, a buildup of foul, a buildup of chemicals that are reacting, the longer they're in there, what can happen? And so you think about the flow being affected, but then you say, what if, what if, what if? You then focus on the consequence, you know, and then it's, if it is acceptable, do very little, but if it's not acceptable, what are we now going to do to mitigate that? So it might require more sensors, more gauges built into the system to be able to give you that information so it can then respond in a quicker time. But nevertheless, look at the consequence. Here, if we have cavitation in the pump, P1, with possible damage if the lack of flow is prolonged. So let's say there's a blockage, again, inside the pump, and it's supposed to be delivering fluid from one to another, to a tank. If that's not doing its job, can you bypass it? Can you take it down to a different pipe system through another pump to deliver it to another part of the tank? So what's your plan B? Because it could well be the longer that chemical or gas is stored inside a pressurized system, and the pump's not working in one part, it could have an impact on the other parts of the machine. And then you look at if the existing or plant controls are unsuitable or inadequate. Focus on failure. Yeah. If it's not good enough, what do we do to improve it? Change the design, improve the design. So it continues through that, reviewing all possible deviations from it, and that's the purpose, key purpose of it. But it's also that critical safety link. You know, the higher the risk, the more that's needed. So look at the typical compromises. What you see on the information that's on a drawing perhaps doesn't give you the full amount, so maybe more detail is needed. Sometimes the as-built drawings aren't quite as they should be. Maybe it needs some more definition. Subsystem designs, it perhaps needs the bigger picture in one drawing, and then another drawing as a smaller subdivision, and another drawing as a subdivision, another one, so that you can look at each part of it within the package. The equipment itself and the chemical specifications around it. So again, link it to reliability, link it to corrosion, how the use of a gas or a fluid under pressure, what can it do to the pipework, the tank, the gauges, the valves, and so on and so forth, to increase potential risks. Bespoke equipment designs and details, so the person that's using it knows exactly the limitations, the capabilities, what it can do, and replacement aspects around it. Information about it in terms of serviceability, and then logic drawings that show from A to B, from B to C, from C to D, step by step on what needs to be done during a controlled movement and during shutdown, and the variations on it. So there's no misinterpretation of how that information can be used. And then, as I've been piping on about quite a lot now, how is it then used in not just operation, but in maintenance procedures? Because as we know, during maintenance activities, things can go wrong. So it's important that this study, this HAZOP study, is used in a proactive manner. It creates the opportunity for people to look at these issues and stimulate the ideas around what needs to be done. So the team will then get together and decide on what's acceptable, what's unacceptable, and what more needs to be done to mitigate the consequences. So, as I said before, team approach should be carried out under guidance initially, early days, so the team work well together. There's always that concern that the bigger voice, the bigger personality will perhaps push their point across at the expense of someone else who's quieter, who's perhaps more knowledgeable, more capable than they are, but doesn't have the opportunity to be able to put the point across in such a way. It is crucial that technical expertise for the study resides within the project team. So you're only as good as your team. The team should include an independent leader and secretary, the various engineers involved, the design and the project manager, so they can see the reasoning behind and justification of why it's been developed in a particular way. The people who are going to end up either running it, operating it, or supervising it. Maintenance staff, because of the risks. Usually, kind of like the what if bit, but often I've seen with HAZOP studies, they forget to bring in the health and safety advisor, the competent person, at their peril in some respects, because you'd hope that their knowledge, someone like yourselves who are working at a level 7 masters, would understand the legal perspective, but also understand how you interpret safety management systems, and then how they are applied, and then how they're checked, inspections and audits. And those things are important parts of making sure that it's brought within the HAZOP study. And then finally, the person who's going to rubber stamp it to say, okay, there might be a designer, it's a new design, maybe they're putting the name to it, or it's the overall chief engineer of the plant and the process itself. So whoever that is, they need to take ultimate responsibility for it, and therefore major part of the team. But the important thing is, because you justify something, it is recorded, so that then it can be used later on if there's any variations, or if someone's trying to reduce the budget and says we need to cut this as a result, you can then say, yeah, but when we did the HAZOP study, it was quite clear from the study that this was essential, and therefore you can't cut down on that particular resource or budget. It has loads of benefits. I'm not going to read them out, but you can see them there. Yeah, so for me, if it's a high risk environment, it should be adopted. So, like I said, this was taken from an article that a gentleman from Turner and Townsend did a couple of years ago, and I thought I'd utilise what they do, because they were kind of using it as a bit of a pitch, should we say, in terms of this is how we do HAZOPs. If you use us, we will use a competent team, we'll use people who know what they're doing, we'll talk you through the process, we'll help you to facilitate it, and so on. So because of using it, just like referencing and citing others, I thought it was only fair that they should take credit for my interpretation of HAZOPs. Okay, so I'm just going to finish off this session with failure mode effect analysis. Again, similar to HAZOPs as such, but maybe they were introduced slightly earlier, but there's a lot of common ground here. Initially, it came from US military. It then was taken on board by Total Quality Management Series. It went through NASA, aviation, automotive industries, and then it became quite a norm to use this, particularly from a design perspective. And then maintenance. Yeah. So failure mode effects analysis is a method that reveals the failure modes, considers the domino effects of the different component parts and what can happen. It searches for the weak points in materials, manufacturing process, and subsystems. Yeah, so that in itself is interesting to read, the limitations of a particular material. So one of the examples we saw earlier was changing steel in a pipe system to mild steel, a much weaker steel in an environment of corrosion, and also had chemicals going through it. So there's that aspect. Then there's the process itself. How does it work? What's taking place? What does it take A to B to C to D, what's parts of it, and where are the safety critical parts to it. And then thinking about the subsystems, which are tells you information about, how do we get that information, or what are the indicators, what do the gauges mean, how is the control panel telling us something, and then how does it influence the behavior of people interacting with it. So it looks at the big picture, steps back a little bit, but then it looks into the more specifics stage by stage. Systematic problem solving kind of approach, the typical you would expect from total quality management, and they'll say, if it can go wrong, what will happen? So it looks at reliability from an engineering perspective, safety from an engineering perspective, and also quality control. It asks that question, what could go wrong? And it looks at how similar products or processes have failed in the past, learning from disasters. They have that historical information about different component parts and the way that things work, the process, the manufacturing process. And as a result of that, they use it to improve best practice. And then the best practice becomes the norm. And again, if you're in a HAZOP environment, or if you're in a COMAR environment, if you want a license to operate, FMEA is a classic example of how you would show and justify that decisions have been made to reduce risk. So quite often the licensing authority will ask for copies of your FMEAs before issuing the license. So giving the example, physical characteristics of materials, you could assume a component will fail in 200°F, if it has information that says from a thermal plasticity point of view, it's only rated to 140. So if you're going to put it in that material in an environment where it could be increasing temperatures to 200, then there's a potential failure. So take account of that, look at the characteristics of that material and say, is it the best one for that job in that environment? So once you've thought through that, how could it fall out? How could it go wrong? Make changes to decrease the chances of that happening. If we take our material, perhaps we say the limit we have is 120 degrees. Lessen the impact the failure will have on the rest of the system, and also a backup plan when we consider that. So what is that limitation, and how then can we learn from it and use it? So the end goal is to eliminate, or at least minimize, chances that the system will have severe breakdowns, knowing the potential weaknesses and the potential effects, cause and effect, on the whole system, and then deciding the parts that can be adjusted to make it more reliable. So again, we can maintain things, but we need it to be reliable from the word go, and then once you've provided it, fit for purpose, needs to remain fit for purpose. So if we look at diagrammatically, there are the critical versions, FMECA, so it's got a critical analysis part of it, but it still follows the same route. You study it, you look at where it can go wrong, you quantify it, and then you identify what's needed to prevent the failure. And in some cases, they either have a logic diagram or some other means, a block diagram that shows step by step how different components, how different pieces of equipment, different materials are used in the system. And then you can say, what if, what if, what if, and look where the bottlenecks are, look where your failures could have its biggest impact. And as a result of that, put in place the backup plan. And if you do use, like you would in a fault tree analysis, which works hand in hand with this, if you wanted to, you could then say, well, you've got your AND gates and your OR gates, look at the series or this parallel approach, and then decide, well, maybe we need to design more into it to avoid that particular situation. Step 2 is identify the failure mode itself. So now that you've done step 1, use all that information and then think about the parts, systems, the poor performance, the reduced functionality, and the failure to complete the intended function, the what ifs. Step 3, then you look at the cause and the effect. If it propagates, if it gets worse, if it goes through those nodes, what can happen further downstream? So if you've got a pressure buildup because pump is not working, and then it builds up and builds up. Could it just break the pump and the rest of it stays inside the piping system of the tank? Or could it just be that there's a safety valve fitted, it takes a new route, it bypasses that pump, and it goes to another area? If I'm doing so, does it create something that's safe, or is it going to fail in an unsafe condition? So we invest quite a bit of time in that to make sure it's a robust system, and it looks at a variety of different error potentials. So human error, material defects, and incorrect engineering requirements. And again, when you look at some of the disasters, these come up time and time again. The culture of the organization itself, the indecision that was made, the one key person that was supposed to make that decision perhaps chose wrongly, or error, or violated, whatever that was. The materials, swapping it from one to another and not realizing the impact. But the incorrect engineering requirements, oh, that comes up so many times. Yeah, we should have put it in this way, but we forgot, or we changed it, or we had a different approach, and all of that encouraged the potential for failure. Step 4, rank it. Give it a rating of, in most cases, 0 to 10, and it's somewhere along the line. It gets quite pedantic. What's the difference between 6 and 7? What's the difference between 5 and 6? Yeah. So the important thing for me is that the people who are making that ranking have an understanding and collectively agree what that rank will be, or that rating, and it then links to action that should be taken afterwards. So you have your first, then you have step 5 and step 6 that also rank or rate the risk issues as well. So look at the impact on users, downstream operation, the environment, and anyone else that could be affected by it. And therefore, cost, physical safety, time loss, damage to equipment are all considered in making that judgment. Assign those rankings. For example, let's assume the failure is substandard. What can happen? So you have another 0 to 10 rating, and from that it will determine the actions necessary, which is step 6. Evaluate and assign failure detection ratings. How easy is it to see with the information you're given, or the control panel, or the gauges and the instrumentation? What does it tell you? How easy is that to see? And then how easy is it interpreted, so that how easy is it for them to take action? Yeah, so 4, 5, and 6 play an important part. And this one could sometimes be overlooked at your peril as such. But again, 0 to 10. Now, we've had 0 to 10 on 3 ranking or rating areas, which means that when you come to multiplying all 3, the smallest amount you can have is 0, so it's no risk at all. Or the biggest risk can be 10 times 10 times 10, which is 1,000. Okay, so somewhere you also need a rating factor that indicates if it's between 600 and 1,000, then it's high risk. Maybe if it's between 300 and 600, it's medium risk. Anything below 300 is an acceptable risk. From that, action needs to be taken. Hence, the RPN is stage 7. RPN is the risk priority number. So once you've calculated those 3, you end up with the RPN, and then you'll use that to define high, medium, or low risk. And the more important issue is to rank and prioritize that risk priority number. Yeah. So from all those design issues, you can then prioritize what needs to be done in order to make it acceptable and safe. Step 8 and 9, they pull them together. It's all about taking action. Who's going to take action and by when? And then number 9 is recalculate the RPN as a result of those changes, those improvements, those reduced risks. So as simple and easy it is for me to describe it, bear in mind what I was saying at the beginning. A good team will debate this throughout, and some projects can take months to get through the failure mode effect analysis for one project, because it has to be right. And bear in mind, if you are a COMAR site, you need to show evidence of this in order to get a license. So from that, you'll look at failure, your planning, how you can control it, and then you'll make it as safe as you possibly need to. Quite often, it is what some would say is root cause analysis. It's a robust system, implements a preventative maintenance routine to check things further on. So there's need to be a system and a procedure to follow through with the completion of the FEA actions. Who's going to do it and what they're going to do about it. Okay, so that's the end of part 3, should we say, which was summing up everything we needed for learning from disasters. And hopefully now you've got an idea of what we're looking for in the assignments, should we say, because HAZOP and FMEA features heavily in that. But as you know, you can always contact me for further information and discussion about any of these key points. Thank you for your time as usual, and good luck in doing your assignments.